Okay, I want you to find this sheet, which is back in your binder. It's the first sheet that I gave you with all the kinematic stuff on it after we did the two big equations, the delta D equals VI delta T plus 1/2 A delta T squared, and the VF squared equals VI squared plus 2A delta D. Remember that first night I think I assigned you like 1 to 7 or something, and then I assigned you down to 12, and we've done them all except the very last one, number 18. So we need to look at it because a number of you said, oh, I'm sad that kinematics is over. Well, the good news is kinematics is never over. I give you permission that you can use those equations throughout all the rest of this course and the grade 12 course too, and really the rest of your life. I had left number 18 until the end just because it has an extra little twist in it of a graph. And so now that there's a long weekend coming up, I thought, well, here's a good time. Okay, so find the sheet. If you can't find it, it is under handouts in Teams. Okay, it's called Displacement, Velocity, and Acceleration Problems. And it's the very last question. And I want you to do it the way the question asks you to do it. Okay, so it says there's an express train traveling at 36 meters per second, and it's accidentally sidetracked onto the local train track. The express engineer spots a local train exactly 100 meters ahead on the same track and traveling in the same direction. Okay, so if we were to draw this picture, right, the express train is behind. The local one is in front. This distance, I believe it said, was 100 meters. Okay? So if you keep reading, it says the engineer on the express train jams the brakes on and slows the express train at a constant rate of -3 meters per second squared. So they're giving you the acceleration of the express train. Oh, they also gave you the initial velocity. Sorry, I didn't write it down earlier. Express train traveling at 36 meters per second. Okay? So now it says the local train engineer is unaware of the situation because he's traveling this way. He's not looking in his rear view mirrors. Pretty sure trains probably don't have, well, I don't have a clue actually. But he doesn't try to speed up or anything because he doesn't know he's going to be rear-ended, or could be. If the speed of the local train, so it'll be a VAV, is 11 meters per second, will the express train be able to stop in time, or will there be a collision? Okay, so now it says to solve this problem, and this is how, I remember I said I want you to do it the way they tell you. So to solve this problem, take the position of the express train when it first sights the local train as the point of origin. Okay, so this is going to be your point of origin, your 0 spot. Next, keeping in mind the local train is exactly a 100-meter lead, calculate how far each train is from the origin by the time the express train comes to a stop. So your first step is to find out how long does it take the express train to come to a stop, and then once you do that, find out how far did the express train travel. In that same time that you just found, use that time over here to find out how far did the local train travel, remembering that you need to add on the 100 meters because it has a 100-meter lead. Okay, so in part A, you're going to get the distance the express train traveled, the distance the local train traveled. You're going to look at those two distances and you're going to decide, is there a collision? Okay, so A says, based on your above calculations, would you conclude that there's a collision or not? Okay, so that's part A. Now in part B, it says, to verify your answer and to ensure that there is no collision taking place before the end of the 12 seconds, spoiler alert, keeping the origin as you did above, calculate the position of each train at the end of each second after sighting until the express train stops. So you're going to do a little chart. Okay? And so this is going to be express. It's delta D. And this is going to be the locals, delta D. Okay. And it wants you to find these delta Ds for each second. So 1 second, 2 seconds, 3 seconds, 4 seconds, all the way up to 12 seconds. Okay? How do you do that? Well, you take 1 second and you sub it into the delta D express equation that you had here, that you had put your time in for. And you get a distance and you write it right here. Then you sub 2 seconds in and you get a distance and write it right here. And then you sub 3 seconds in, etc., all the way up to 12. And then you do the same for the local. You sub it into the equation that was here and make sure you add the 100 meters on. Okay, and then sub the 2 seconds in and the 3 seconds in. So you're going to have this nice table. Okay, so it says make a table showing the distances each train is from the origin at the end of each second. Here's our table. Then it says plot these positions on the same graph and draw the two lines. So then you take a piece of your graph paper that you have from back at the beginning when we were doing drawing to scale, and you're going to make a full page graph, not this itsy little bitsy graph up in the top corner. You're going to do a full graph, okay, on your graph paper. I'm just going to sketch it here. Okay, so you're going to make your graph. On this side will be delta D's. Down here will be delta T. And you're going to plot them for the express. So however far the express went in 1 second, and then in 2 seconds, and you're going to plot them all, and then you're going to join them. And then you're going to do the same for the local. And remember, at time t equals 0 here, the local is at 100 meters. Okay, and then because you've added 100 on to everything else. The express at time t equals 0 is at 0. But the local is going to start up here. And you're going to plot them. And you're going to connect the points. So you could plot them in 2 different colors. Okay, that's part B. And then part C says, use your graph to check part A. What can you conclude? Okay, so whatever you concluded from part A, now look at your graph and see if it supports it. Okay, so that's one of the things I would like you to work on over the weekend, please.